Good morning, good afternoon, good evening to people around the world. This is Martin Hubel, your host of the DB2 Night Show. As I go back to my headset and I get that nasty message on my screen, I'd like to welcome to the first show of Season 12 of the DB2 Night Show. I'm your host, Martin Hubel, and my special guest today is Kai Stroh of UBS Heiner. That should say UBS Heiner. I made a mistake on your company name there, didn't I?
Well, yeah, that is the UBS is actually a bank from Switzerland. People sometimes confuse us with the bank.
I know.
That is not us. Our company is 1 year older.
I actually, I just fixed that.
But they still sometimes send us weird emails about, us using their trademarks and names and stuff like that.
I've actually been in, I have been in Basel in the UBS offices. So
okay.
I know people at UBS, and they're really nice people. So,
Basel, that's right at the borders, the Swiss-German border.
And I actually stayed in France when I was there. It was a bit of fun.
You definitely want to do that. It's cheaper. Switzerland is really expensive.
Yeah, I remember the big specialty in the hotel was carp frites, and everybody says, "Oh, that's terrible." And I said, "Oh, it tasted really good to me." Well, what do I know? All right, let's move along here and have some show. Let me get the right button here, and I can flip forward. There we go. Normal housekeeping here. This is your show. Here's our Twitter feed on DB2, our hashtag DB2Night on Twitter. Please make sure you follow us so you get updates on shows coming up. That's a great thing to do. We also have our LinkedIn group, and now we put our replays up on YouTube. So if you don't want to download anything, you can watch us on YouTube. We have our own channel. And as always, here's our disclaimer. I do recall having to read this over and over again. I got pretty quick at it. However, let me just say, we're being recorded. There are trademarks, and they belong to the respective organizations, and we respect copyrights, and this broadcast itself is copyrighted by DBI 2020. The rest of our quick announcements. Here are our upcoming shows. We've got a brand new presenter for the DB2 Night Show next week. Daniel Snoddy is a manager within the IBM Toronto lab, and he'll be looking at graft and rest with DB2. So that if you're interested in developer topics and graph and that sort of thing, that's going to be a real key thing. As well, for LUW, we've got a Docker cookbook by Ian Bjorhovde of Extivia, and I don't believe Ian's been on the show, but he's a very good presenter and a popular presenter as well. So we're excited about those two shows. Our next DB2 on Z show will be from Patrick Bossman of the IBM SVL. He's the guy when you want to talk about application development support for DB2 on Z. He's the guy, and we're excited to have him back as well. That'll be another great show. We do have shows forming up for November and December. For example, Dan Luxtich will join us on DB2 on Z in December, and also Christian Malero has also been on the show before, and he'll be joining us in November. So we can have that to look forward to as well. As always, there's our founding sponsor of the DB2 Night Show is DBI Software, and there's their performance webinar on their website. You can follow that link. And we're going to have some new commercials from DBI starting with our next show. And there will be 1 to 3 minute commercials that we'll be having. As we always had those in the past. We've recorded new ones, and they'll be available. So we can look forward to seeing what's going on with the DBI Performance Suite. Congratulations to Richard Urich of Nationwide. He's our gift certificate winner from last June. That was sent out some time ago. We'd like to announce the name and let you know that your participation on the show can result in a gift certificate. And I also want to announce that with a good typo in here, yours truly is now an IBM Lifetime Champion. which means that IBM thinks that I've done a lot for the DB2 community. I would say that that might be true, seeing as I've been involved with Guide local back in the days before there was an IDUG, and then with IDUG since 1989, and then with our local Central Canada DB2 user group, and a whole bunch of other things with presentations all over the place. So now I'm a lifetime champion. It means I do not have to fill in my activity reports, and I'm automatically made a champion for the next year without doing IBM paperwork. And they also call on me to do other things. If you watch the DB2 or the Data and AI forum this week, you saw me as part of that as well. I was in a recorded interview with the lab director of Toronto and Noel Johanna of the Forester Research Group. I was recorded on Wednesday to do that. So that's big news. Here's a brief look at one of their new screen mockups for the DBI toolset. DBI did do a infomercial, as it were, for an hour in July, where this was shown amongst a full demo for an hour talking about the new products. So if you're a DB2 LUW customer, it would serve you well to have a look at this information. And there's our sponsors, DBI and me. Now, we always try to put a bit of humor in here. For a while ago, I put dear old Charlie in, and I had to put him in this time because the next slide is something really important. We're in the middle of COVID, and there's nothing like looking at a puppy to make your day. And here's old Charlie. He is now 15 and a half years old. And what you see him doing in the upper left-hand corner is something he is very good at. He's very good at sleeping, and you can see that in the bottom here too. He will sleep in anything, including shoes. You just got him groomed. He was really, really fluffy, and it was time for a grooming. And I have pictures of him looking pretty much like he does here. And he's carrying along, but we have a new neighbor. So you want to see, this is a 15-and-a-half-year-old dog. Here's a brand new puppy moved in across the road. Our good neighbors over there. I went over and saw her this week, Ember, and she's a fox red Labrador retriever, and she's wrinkly, and she's about 2.5 months old, and she's just the cutest thing ever, and she's going to be a great addition to their family. She's still settling in because she just got here from Winnipeg. There's a real shortage of dogs right now in North America. As everybody is at home, everybody wants somebody to spend their time with, so there's an awful lot of people out getting dogs. And but our friends Jim and Patty across the road have had Labradors for the last 20 years, so Ember is just the next in their line of pets. Their other ones died of old age. Okay, it's that time where we do our audience polling questions. And so let's get the first poll up today. And I put on a fun poll just to let people see, have a chance to vote on what's going on. And just to see how this is going down. There are times during this COVID thing where I feel I've got a condition called COVID brain, which means if there's something that I could do today, I might as well put it off to tomorrow. I don't know, there's nothing like, or forgetting things or leaving things half done. So, yeah, I think we've got enough responses closed. I'll close that and share the results. And 12% of the people always work from home. 41%, it's changed a little bit. 41%, I used to go to I was in the office regularly, and 6%, sorry to hear, I lost my job. We're kind of lucky in our immediate nuclear family. We've only had one of our grandchildren lost a job working as a waitress in a restaurant, but the rest, and that job has slowly been returning. So we'll hide that, and we'll move on and look at the next one, which is getting into our standard questions, is what's the highest version of DB2 you have in production. And it's nice to see that the older stuff seems to not being answered these days, and that's a very good thing. Just to give people another 10 seconds to vote on that. And we'll close that off and share the results. And people are getting current. That's a great thing. 40% of our audience is on newer stuff, and only 20% are still on version 11. So that's great to see. The other thing I should do is to make sure I check my question and answer queue, and that's empty. That's a good thing. I'll keep up with that. And what other DBMSs do you have? I think I even got this now that you can actually have multiple responses. So I'm imagining everybody's going to check every single box. And I think IBM would sometimes like me to make sure the other mainframe DBMS there is only IMS. I actually did some work with a company that was doing IMS tools still. And they've become part of Rocket Software. So we'll close that, share the results. As expected, everybody has DB2 for C because you're here. And the other 81% roughly there on the other mainframe DBMSs. And now we get into our questions relating to today's show. Have you ever had to back out a series of transactions? Interesting. I thought some people might say it was hard. Oh, some people are now. Now I feel better. I had one where it didn't have tools, and somebody had inadvertently meant to make it test a change in test, and they actually made the change in production, and it changed all of the address line ones to one specific value. Later, I had to go back and back out 362,000 address changes. That was wow. that was not my most fun day ever.
Did you recover the whole table space, or did you do it individually?
You couldn't do that because people were still adding, new customers were being added every minute, and and old customers were going in and fixing their addresses manually. So they said only fix the ones that no one has touched. So it took me a long time to come up with a special piece of SQL from a backup of the table. Not my most fun ever. And so here.
Nowadays, you could probably use temporal tables for that.
Well, maybe, but again, I guarantee you, if you had temporal tables, they would do it on a non-temporal table just to make your life more interesting. Oh, the things that can happen. Sometimes I think I've lived too long. Most days I think I haven't lived long enough. There's still more mistakes to make out there. Have you had to ever recover an accidentally dropped object? And we're getting that done. Seeing the answers there. And I know some people, they literally change if they're using a 3270 emulator, they use a different color for test and production to make sure they're working in the right system.
I do that.
Yeah. Green for test and blue or something for production.
Right. Right.
Like that. All right, let's close that off and share that result. Some people said it was hard. Some people said it wasn't too hard. And other people said, no, lucky you. And I guess that's it for questions. Thanks for participating, everyone. And I'll go back, and now we'll turn things over to you, Kai. We'll make you the presenter. So let me just let me do that just now. Just got to find the everything sort of Oh, that's the audience view. There we are. Where's the attendees? There they are. And we'll make you the presenter. You should now have a message on your screen.
Not yet. No, there it is. Okay.
Yeah.
Just gonna show the whole screen there. It's the easiest way to do.
Yes, that works just fine.
So you should see the title slide called Exploit DB2's Log.
Yep.
So first of all, lest I forget, congratulations on your lifetime champion award. It is well deserved.
Thank you.
It's a great achievement. I'm nowhere near to getting that, but who knows? Maybe one day IBM will notice me. This presentation is called Exploit DB2's Log, and as you can probably see in the top left corner, it says ULT UBS Log Tracker. That is actually the name of a product that we have, but this is not going to be a sales presentation. I have removed all the slides that had anything to do with the product itself. It's only that line at the top that stayed there. This is going to be a pure technical educational session. I want to show you a little bit about the DB2 log and what's actually inside. So not so much, I'm not going to talk about the active log data sets and the archived logs and how you should size them and, you know, archive to tape. I'm not going to be talking about that. Instead, I'm really going in there and we're going to look at log records and what they contain. And I think there's probably some interesting stuff in there, whether you have previously looked at the log or not. If nothing else, it makes you maybe understand a little better how DB2 ticks and what really makes DB2 work inside. So first of all, a little disclaimer here. I do not work for IBM. I work for UBS Heiner, and I did not have anything to do with any development in DB2, so nothing of the DB2 code is from me. I have no insight into the code. Everything that I tell you here is based on what I have found out working on, well, the products that we have. And some of it is documented, some of it is not. The stuff that is not documented took me a while to figure out. I want to stress the last part here. So there could be some stuff in here that is simply incorrect because I just don't know any better. I hope everything that I tell you is accurate, but if there's something in here that, you know, I say this is how it works, but in reality DB2 does it a little differently, that's just because I don't know any better. So, and with that, let's jump into the presentation itself. So let's talk a bit about the purpose of the DB2 log. The log is something that is not exclusive to DB2. So every relational database system, or practically every database system out there, has a log. It is something that is a protocol of everything that is happening in the DB2, and it's extremely essential for maintaining, like I said, the consistency of the database. DB2 itself thinks the log is so important that it has multiple copies of the log. So you have dual logging, you can turn that on and off in the cparms. It's usually a good idea in the production system to have that on, so that if one copy of the log gets damaged or lost or something like that, there is another identical copy that DB2 can use. So the trade-off of having twice the disk space for the log is something that DB2 considers it worth it, basically. Since the log is a protocol, DB2 will only ever add log records to the end, basically. So it will never update any existing log records and change anything in there. And it will also never delete any log records that have previously been written. It's just one continuous stream of data, basically. And of course, DB2 starts logging the moment you install DB2 and first start it up. That's when DB2 starts writing log records, and it basically never stops. So everything that you do in DB2 goes into the log. I should probably say everything that you do that changes something in DB2, because the log will not contain any information about read access. So if you do a select on a table, that is not reflected in the log. Also, if you try to maybe do an insert and that insert is rejected by DB2 because you don't have the authorization to do that, that is also not reflected in the log. So only things that actually change are written to the DB2 log. And that's one important thing to keep in mind, because if you're doing log analysis, you can see who changed something, but you cannot see who accessed something and who read some of the data in your tables. One thing that some people don't really realize is how important the log also is in maintaining the asset properties of DB2. So every relational database system has these ACID properties. ACID, that stands for atomicity, consistency, isolation, and durability. And those are 4 very important qualities of a database system. And the DB2 log is actually essential in maintaining 2 of these 4 properties. And the 2 properties are atomicity and durability, as you can see here. Now, as for atomicity, the DB2 log allows DB2 to roll back a transaction. So when you do things, when you do insert, update, delete, and then you decide, oh, you know, this was wrong, I didn't want to do that, you can say roll back. And what happens is that DB2 will access information in the DB2 log in order to roll back the things that you did. So when you do an insert, it goes directly to the log, even before you say commit. And then later when you say rollback, DB2 retrieves that information that an insert was done from the log, and that way it can roll back your transactions, and that can guarantee that the entire transaction with everything that has been done so far is rolled back. So that's the atomicity aspect. So either everything that was done in the transaction is written to disk or nothing is, basically. And the other thing that the log enables DB2 to do is maintain durability. Durability means that the moment you say commit and DB2 accepts the commit and returns SQL code 0 for that commit, it means that your changes are safe. And if DB2 should crash like a millisecond later, it doesn't matter. The commit was okay, the commit went through, and that means the moment you bring DB2 back up, it will restore that change, it will bring everything back to where it was, and that change will be there because DB2 has confirmed the commit. And DB2 can do that because the log is a write-ahead log, and that means that changes are written to the log first and then to the table space. So basically everything that you do goes to the log before anything else happens, and that allows DB2 to guarantee that durability aspect. So those are 2 important aspects where DB2 really uses the log. Of course, DB2 also uses the log for other things, and the most prominent thing is probably when you recover an object, when you recover a table space, then DB2 will use image copies to establish a baseline and then apply log records. That's a no-brainer, everybody knows that. One thing that is also interesting to know is how exactly does DB2 write records to the log? Everybody knows that there is an active log and an archive log, but some people don't know that there's actually like a third part to that. There is a buffer that is fixed in real storage, and log records are written into that buffer in memory as you're doing your transactions, as you're doing your inserts, updates, deletes. And when this buffer is full, then of course it gets flushed to disk, but it also gets flushed to disk when you do a commit. And this is a synchronous write, so the commit will not go through if there's a problem writing that buffer to disk. And that means that even though this buffer is in memory, in main storage, there's still no problem if DB2 should go down or if there's like a power failure, which basically never happens these days, because the moment you say commit, DB2 makes sure that everything is written from that buffer to disk, and then, only then, will it confirm that commit. And this is a big difference to, like when you do an insert, of course, the insert goes to the log, but it also goes into those pages in your table space. And those pages are not directly written to disk. Even when you say commit, DB2 does not necessarily write those pages to disk. They can stay in the buffer pool. But that doesn't matter because all the information about all the changes and what the page should look like now is in the log, and that log is on disk. And that allows DB2 to restore or to recover that page if it ever needs to. So that is one very important thing to know about how DB2 logs writes log records, basically. And then, of course, we have the fact that the active log is then copied into archive logs, and this is done asynchronously, of course. DB2 does that automatically, or when you tell it to by issuing the archive log command. So that's the easy part, basically. That's the outside view of the DB2 log. But now we really want to go in there, and we want to look into a log record, and we want to look at the different fields that we have there and what we can read there and what we can see there. So we're going right in and we're going to look at the gory details of the DB2 log records. Let's have a quick overview here first. So I mentioned that the log is basically a continuous stream of data, but it's still basically split into individual records. Now, these records consist of a header, and then depending on the type of record, there can be one or more different sections that contain additional information. there is no delimiter between the log records. So it's just one log record after log record after log record on the log. And DB2 keeps track of which log record begins at which position by simply having a length field. And the beginning of one log record plus the length field, that's basically going to be the beginning of the next log record. And that beginning of each log record is also what we call the RBA, the relative byte address. It's a number that always counts up, never goes down, and it basically represents the offset of a log record in the let's call it the eternal log, right? So of course, physically, DB2 divides it into archived logs and active logs and individual data sets, but you can think of it as one continuous stream, and the RBA of a log record is the offset of each record in that eternal log that DB2 has written since it was first installed. Every single log record that you have begins with the so-called LRH. That's the log record header. There are no exceptions. Every single log record has that. And that LRH, you can see that here. I've broken that into the individual field. Well, there are more fields than that, but those are the most important fields here. We have, of course, a length. We have a type and a subtype. This is how DB2 and also we can really see what this log record really represents. We have something called the URID, which is the unit of recovery ID. Basically, all the log records that belong to one transaction will have the exact same URID in this field. That's how you can tell all the log records that belong to a given transaction. A log record also contains the RBA of the previous log record. This is information that DB2 uses in order to detect if the log is damaged. So basically, every log record points to its predecessor. And then there's another RBA in there, and that points to the previous undo record. Now, what is that? That is basically a pointer to the log record that DB2 would need to undo next if the entire transaction is undone because you did a rollback. And this is important because it can speed up a rollback process. And we'll see why that is later, because it's essentially because multiple transactions can be running at the same time, so it makes things a little quicker. But I have more details on that in a little bit. A log record also contains, or the log record header contains the LRSN. Even on a standalone system, there's always the LRSN in there, which is basically a timestamp. And there's a field for the member ID, which is the, on a standalone system, that's always going to be 0. In a data sharing group, every member has an individual ID, and that's how you can tell which member wrote which log record when you look at the log as a whole. So of course, every member keeps its own log, but when you use something like DSN1 log P and look at a certain time frame, you get all the records from all the members combined. And this is how you can tell which member wrote which record. So these are the most important fields in the log record header. You will notice that the RBA of the log record itself is not part of the header. So the RBA is not written down anywhere. It's basically just the offset of this record, but it's not in any field. So you can't really see it when you look at a log record. Of course, DB2 knows the RBA of each record because for every archived log dataset, for example, it keeps the information in its BSDS what the RBA of the first record in that log dataset is. And then when you use something like DSN1 log P to look at it, it can basically do the math and print the RBA of each record. But it's not part of the record itself, which is something that I found interesting when I first found out about this. Now, log record types. There's a number of different log record types. I don't really know how many there are, probably 10, 12, or even more. But these are the three most important ones. There's unit of recovery log records. These are written by DB2 whenever a unit of recovery, let's just call it a transaction, when a transaction starts. It is also written when you do a commit, and it is also written when you do a rollback. So this is basically how DB2 keeps track of transactions that are starting and coming to an end. And I have also some examples for that. And then there's the data change log records, and these are the ones that are probably most interesting for us because these reflect actual changes to a table space or index page, so physical changes to a page. So typically this would be insert operations, updates, deletes in a table space or index. For indexes, of course, these would be key inserts or key deletes or RID inserts to an existing key or RID deletes. The RIDs being the pointers to the rows in the table space. Now, these data change records can also represent things other than insert, update, and delete activity. They can, for example, represent changes to a space map. So when you insert data into a table space. Maybe the table space is full and DB2 needs to add a new page. So it will also make a change on a space map page to indicate that there's a new page that is now being used. And this change, which is probably only 1 or 2 bits in a change in a space map page, is also written to the log in a data change record. And then there's checkpoint records. And these are created whenever DB2 creates a checkpoint, either automatically, based on your zparm settings. So when a certain number of minutes has passed or when a certain number of log records has been written, DB2 will create a checkpoint. But you can also trigger a checkpoint manually by issuing the set log load 0 command. And the checkpoint log record is not really one record, it's a series of records, and they basically contain a list of open transactions and also the information which transactions has modified which page sets since the transaction started. And this is an important piece of information if DB2 ever needs to do a recovery, because it needs that information. It needs to know which table spaces and which indexes were currently being accessed. And this is basically, well, the name says it, it's a checkpoint. It's a point in time where DB2 knows exactly the current state of things in the subsystem. So I said the most interesting records are probably the data change log records. So let's look at those in more detail. They're written whenever something on a page in a table space or index changes physically. A data change record always contains the LRH, because every log record has that. And a data change record also contains another header after the LRH, and this second header is called the LGDB head. And this second header has fields that contain, for example, the DB ID, the PSID, and the page number. In newer DB2 versions, there's an extra field for the partition. In older versions, the partition number was encoded in the page number. This is, of course, to support the relative page numbering that we now have in DB2 version 12 for our universal table spaces. So these structures, these headers, the structure changes from DB2 version to DB2 version. Things move around. Fields are added because DB2 now needs more information on the log. I have 2 examples later that show you a DB2 version 10 record, and I have the very same record from a DB2 version 11, which has been converted to 10-byte RBAs. We can see the differences there. So data change records mostly describe insert, update, and delete activity. I said they could also describe changes to a space map, but if they describe insert, update, or deletes, they will have a third header, which is called LGB entry. And this header has then fields for, well, the OBID, which in my opinion is not that important. Don't really know why DB2 stores it there. But it also contains information about the slot number in a page. So if you know how a data page looks like from a table space, you will know that it has up to 255 slots. And it's important to put a log record, not at a certain offset, or I said log record, I should have said a row of a table, basically. It's not so important at which position in the page that row is located. It's important that the slot number is assigned correctly, because the index points to the slot number, and that's how DB2 can actually locate the data in a page. So we can move data around as long as we reflect the current offset in that ID map entry, which is at the end of the page. So this is why it's sufficient to store the slot number in the log record. So typically what we will see is these 3 headers in all the log records that describe insert, update, or delete activity. What's also important to know is that the log record does not say something like a column X on this row was changed from A to B. But instead, what the log record will say, it will say on page 27, for example, in slot number 5, the 2 bytes starting at offset 14 have changed from hexadecimal something something to another value. So they really describe the changes in binary. Which also means that it's really difficult to read those log records if you don't know how to interpret them correctly. And interpreting them correctly is not exactly trivial, but we're going to do it in just a moment. So how do you actually look at log records? I mentioned DSN1logP a couple of times. This is the tool that comes with DB2, and you can use that to basically get a human read, well, not exactly human readable, it's more or less a hex dump, but you can see some of the things in your log records. So what you do in order to run it, you specify a start and end RBA. Now, if you're running a data sharing group, it's going to be a start and end LRSN. And you can also specify some filters. So you can say, I only want to see log records for a certain DB ID or PS ID, because maybe you're only interested in one particular table space. And then DB2 will simply hide all the log records that do not belong to that object. And that makes the output much smaller and much more readable. You can also filter by URID. So if you know the URID of the transaction that maybe changed something that you want to change back, you can tell DSN1LogP, please show me everything from that URID. And then you will see the begin UR record, followed by all the data change records, followed by probably a commit record. You can also filter by log record type if you want. I've never found that particularly useful, but the option is there. Now, the output of DSN1LogP is, like I said, essentially a hex dump. Some of the fields are formatted, so you can read some of the stuff. The rest, not so much. The rest is pretty hard to read. So, with that in mind, let's now dissect the log record. Let's take one and take it apart. Here's an example log record. I will zoom in just a moment. This is something that you could, for example, find in DB2 version 12. This is a record that was printed by DSN1LogP. So on the bottom half of this slide here, this is the typical output of DSN1LogP. This particular record represents an insert of a row into a table space. And what DSN1LogP formats, and you can see that in the three header fields there, or the three header lines, I should say, is it formats parts of the LRH, so some of the fields in the log record header, and also some of the fields in the LGDB head structure. You can find a dissect which has those structures in your SDSN Max library. And the member name is DSN-DQJ00. It's a weird font that I'm using, those are the zeros at the end, not O's. And this is, like I said, it's a dissect that has all the information how to read these log records. It can still take some time getting used to the information in DSN-DQJ00 and, kind of get a feeling for it. But essentially, all the information is in there. So let's look at the parts that we see here. So zooming in here now. One thing that we have here in this particular offset, it's not the beginning of the log record, it's somewhere in the middle. You see this 0600 that we have here. This 0600 indicates that what we're looking at is a data change record that contains both redo and undo information. I will explain later what redo and undo information is. For now, let's just leave it at that. Then this is followed by another 2-byte field. This is 0001. In this case, this indicates that this is a basic data page change. This is what DB2 calls that. So this is the most basic log record that you can get. It's something that represents a change in a data page, and the log record has undo and redo information. And every time you have that, you will see this 0600 and that 1 in the next field here. Over here, we have a RBA. And this is the URID of the log record. The URID is essentially just the RBA of the first log record that belongs to this transaction. This RBA automatically becomes the URID for the entire transaction. So the URID is nothing more than an RBA, and this is why it looks like an RBA here. This is a DB2 version 12, so we're looking at a 10-byte field here. I could tell DSN1LogP to show me exactly that log record here, and this would basically take me to the very first log record of this transaction, which will always be a begin UR record. Then over here in light purple, we have the RBA of the previous log record within this transaction. I mentioned that DB2 chains those log records together, and this is basically a pointer pointing backwards in the log to the next, or I should say the previous log record that belongs to the very same transaction. And if you do a rollback, then after undoing the changes from this log record, DB2 will then jump to the RBA that is here in light purple, and it will go to that log record, and this is the next one that will be undone. So this is basically how that works. In a slightly darker shade of purple, we have the LRSN of this record. This is basically just a timestamp. It's again in the 10-byte format here because this is a DB2 version 12 record. Here in light blue, we have two fields actually. It's the DB ID and the PSID of the table space that was modified. And you see that this is no longer in the LRH. We're already in the LGDB head structure because this is a log record that is representing a data page change. So we need to know which object was modified, which table space. This is, of course, hexadecimal. So the first 2 bytes are the DBID, 0125 hex, and the next 2 bytes, it's just number 2, also hex, which is 2 in decimal. This is the PSID of the table space. So this is the object that was changed. And this is followed by the page number that was modified. And this is page number 2. Page number 2 is typically the first data page in a table space, unless there are system pages or dictionary pages, which could also occupy that page number, in which case the first data page would be further down. But in a very simple scenario, page number 2 is our first data page. So this is what was modified. And then I hope this is visible. It's in a pale gray. This is another RBA here. And this one is interesting. If this log record is a so-called compensation record, I will explain what that is in a moment, then this is the RBA of the log record that is being compensated by this log record. Sounds a little complicated, but I have an example of how that works in just a moment. And then even further down, and this is the part that DSN1LogP no longer tries to format or anything. This is the LGB entry structure that we're now in. Since this is a change to a data page, we need to know which row number inside the page was modified. Well, this is row number 1. So this was probably the very first insert that I did in a newly created table. It was inserting something on page 2 and was row number 1 on page 2. And this is what we can see here. This 01, this is only a 1-byte field because a page can only have 255 rows. So 1 byte is sufficient to store that information. And then we have the OBID of the table. This is OBID 3. And like I said, I'm not really sure why DB2 stores the OBID of the table. It's maybe used just for filtering. I mean, nowadays, most table spaces should contain one table anyway, but maybe if you have multi-table table spaces, you might want to filter by table. You could use that field for that purpose. And then there's one final component, the rest of the log record, basically. So this is the entire row as it appears inside the page, including the 6-byte row header here. Actually, I think I did the highlighting wrong. I think I highlighted the first 8 bytes should not be here. Can I do in PowerPoint? I kind of want to use like a pen here. This should not be here. Okay, so I believe these 8 bytes do not belong to that. That is some other piece of information here. I think it really starts over here. Starting here, this is the row as it would appear inside the page. And the first 6 bytes, so everything up to here, that is the 6-byte row header. The slot number appears here one more time. This is the OBID one more time, but this is now payload. So this is no header field of the log record. This is really the row as you would see it if you were using DSN1 print, for example, and print page number 2 of that table space. And the rest is, of course, the data. So you can probably spot an integer number here. So this is your integer number. It's number 1. For integers, DB2 always flips the first bit and so on. So at that point, you need to know the structure of the table in order to be able to interpret the rest of the log record. Some of the fields I did not explain, so everything that is currently not highlighted also contains information, but it's not that important. So these are the most important fields in a typical data change log record here. This is a version 12 log record, and I believe if I go to the next slide, I thought I had the same log record as a version 10 with the shorter fields, but I may have hidden that slide. It looks very similar, just some of the fields have changed position and some of the fields are a little shorter. Other than that, all the information is also in there. And like I said, the DSN DQJ00 member contains the mapping of this information. Now, when you look at data change records, they're used for insert, update, and delete activity. And insert and delete are simple because the log record will always contain the entire row that was inserted or that was deleted. But for an update operation, it's more complex than that. For updates, the log record contains two images, and these are called the before image and the after image. And they can be part of the same log record, but it's also possible that DB2 splits those into multiple log records. When would that happen? It could happen, for example, if the table row is just too long for one log record. So in older DB2 versions, there was a limit. A log record could not be longer than 32K. And if you have a table in a 32K buffer pool and it has a varchar 32K or almost 32K field, and you update that, you could be looking at almost 64K of data that needs to be logged. So it couldn't fit in one log record. Another reason why DB2 might split an update into two log records is sometimes a row changes position. Sometimes a row even needs to be moved to a different page because the update operation made the row longer and it no longer fits into its old position and there's no additional space on that page. So DB2 needs to physically move that row from one page in the table space to another. Now a log record has this header that says which DB ID, PSID, and page number was modified. And if we're moving something from one page to another, we can't describe it with only one log record. We need to make one log record that describes that a row was removed from this page, and we need to have another log record that indicates that the row was now being inserted into that new page. And this is exactly what DB2 will do. There is a flag that says that this is not really a delete and this is not really an insert, but rather that it's a delete or an insert that is done on behalf of an update operation that was done by the user. This is, when you read that, it's basically your indicator that these two log records belong together and they're describing one single update. But it gets more complex than that because it would be way too easy if that was all that there was to update operations. But it turns out that there's roughly a dozen different ways that DB2 can log updates. And it really depends on if rows get longer or shorter, if rows change position within a page or move to a different page. Basically, DB2 has all these different update variations to store the log record in the most efficient way. So it tries to use the least amount of bytes in order to store the change that was made, and that's why we have so many different variations for updates. There's also a difference if the table has the data capture changes attribute on or not. Data capture changes is something that you can activate for a table, and if you do, then a log record that represents an update will always contain a full row image. It could be the before image, so what the row looked like before the update, but it could also be the after image, what the row looked like after the image. And then in addition to that, there will be a delta, which could be just a couple of bytes maybe. But the important thing is that one log record contains the full row. So that means by looking at that log record alone, you can basically see what the update operation did exactly to the row. But if data capture changes is not active, then DB2 can write a shorter version of the log record where really only those bytes that have changed are logged. And that could mean that if you change a single integer in a table that has a lot of columns, DB2 would really only log the old integer and the new integer, so maybe 8 bytes, and that's it. And nothing else of that row would be logged. And this can be very tricky if you look at that update record and you want to figure out which row was modified because you just don't have the information. You don't see the other fields. You do see things like the page number, and but you have to figure it out from there. And it's really complicated if you want to do it manually. And of course, pointer records can change to pointer records. So there's a lot of different things that can happen when you do a simple update statement, depending on what's really going on physically inside the pages. I think I already mentioned most of that. What's in the slide? I was a little fast there. Oh yeah, for those non-DCC records, so when the table does not have data capture changes, if you really want to restore the full row, you need to identify the page number and the slot number, and then you need to locate a full image someplace else. It's not in that log record, so you need to look at certain different places to find the full image. It could be in older log records. It could be in an old image copy. It could be in the vSAM cluster that belongs to the table space. So it's not impossible, but it's tedious. It takes a long time, and it's really error prone. And of course, the reason why DB2 does that is because that's all that DB2 needs. That's all that DB2 needs in order to apply that log record. It's just those couple of bytes that have changed. DB2 doesn't need more physically to make that change to the page, so why should it log more? So now that we know what the log records roughly look like inside, let's talk about this redo and undo stuff. So I said we were looking at a log record that contained both redo and undo information, but what does that really mean? A log record contains redo information if the information in that log record is important for DB2 in order to apply that change in forward direction, coming from a page that has a status before that change and changing that page in a way so that the change goes into the page. DB2 uses that in a typical recovery process, so it will restore a full image copy and then maybe also incremental copies, and then it will apply all the log records in forward direction up to the desired point in time, which could be the current point in time. It probably is. Usually you do recover to current. So all the log records that contain redo information are being processed. If there should be a log record that only contains undo information, DB2 will ignore it because it doesn't have anything in there that it could use at that point, so it will just be skipped. On the other hand, undo information is something that DB2 needs if it should ever be in a situation where it needs to reverse a change. So for example, if you're canceling a transaction by doing a rollback, DB2 needs to actually roll back every change that you made one by one. The changes that you do when you do insert, update, delete, they go straight into the pages, they go straight into the log. So when you do a rollback, DB2 actually needs to actively undo everything. And what it will do is it will go in backward direction through all the log records for that specific URID, and it will look into each log record, look if it contains undo information, and if it does, it will use that information to bring the page back to a previous point in time. So this is basically what DB2 does when you do a rollback, and as it is doing that, as it is doing the rollback, it will of course write new log records to the log, because rolling back a change means that DB2 changes the pages again. It is undoing what you did, but those are additional changes to the pages, and these will be logged, which is also the reason why rolling back a transaction can create a tremendous amount of log and can also take a very long time. I have an example for that in just a moment. Now, when you say commit, or let's start at the beginning of the transaction. Let's start at the start. When you do your first insert, update, delete, which starts a transaction, DB2 will write the begin UR record, and this log records RBA becomes the URID of all the log records that belong to this particular transaction. And this is followed by all the log records that describe the changes that you made. And then finally, when you say commit, DB2 simply writes a begin commit phase 1. Then there's one record that represents the switch from phase 1 to phase 2, because we have two phase commits. And then, assuming that everything is successful, there's going to be a third log record that is called end commit phase 2. And with these three log records written, your change is, well, it has achieved durability. So it's in the log, and whatever happens next, your change is safe. Here's what that looks like. To keep things simple, I have shortened the RBA to only 3 bytes because I didn't want to work with like 20 hex digits here. So let's just assume our RBAs are 3 bytes long, and we start at RBA 500. What you see here is a transaction that does 2 inserts and 1 update, and then it does a commit. On the log, this is what it looks like. We have our begin UR record at RBA 500. This RBA becomes the URID of all the log records for this transaction. And then the next thing that happens is you do an insert. Now the log record RBA of the insert is then, let's just say every log record is hex 100 bytes long. So we get 600 here as our RBA. The URID is, of course, the 500 that we have here. This log record is flagged to be not a compensation record. I'll explain that later. And there is a pointer to the previous log record that belongs to the same transaction. So the log record at RBA 600 points to the one at RBA 500. This is this little arrow that we have here at the right-hand side. And then you have your next insert, and then followed by an update. And you can see the URID is the same in each and every one of these log records. And the undo next, that's a nice chain of pointers, each one pointing to the previous log record in the transaction. And at the end, we have our 3 log records that represent our commit, begin commit phase 1, switch to phase 2, and then end commit phase 2. This is the very simple scenario, simple transaction with 2 inserts and 1 update. fairly easy to understand. Let's make things a little more complex. What happens if you have multiple transactions going on at the same time? That's something that DB2 allows you to do, but the log is something that is written sequentially. So it's kind of a choking point. Everything that happens in DB2 has to go to the log, and the log is written sequentially. There's only one log, so only one log record can be written at a time. So basically, these log records for those multiple transactions are now interwoven on the log. So there could be a couple of log records from transaction A, followed by other log records from other transactions. And this is what's represented here by the blue and yellow colors. And as you can see, the important aspect is, first of all, you can see the URID 500 for the blue transaction and all the blue log records, and 700 for the yellow ones. And this is the same for all the log records of the same color. And you can also see that these backchain RBAs here, these undo next pointers, basically, they point not to the previous log record, but to the previous log record in the same transaction. So for example, the one at RBA E00 has a back pointer to C00, not to D00. This is important if DB2 ever needs to traverse the chain of log records in reverse order. So this is what it looks like if transactions happen at the same time. By the way, the begin UR record itself has a back pointer to itself. And this is an indicator that this is the first record of this transaction. There is no other log record that was written before that. This is the beginning of this transaction, basically. But this is still pretty easy, basically, because we are only committing our changes. We do not do any rollbacks here. Now, what happens if you do a rollback? If you do a rollback, well, the transaction starts with begin UR, and then you have your inserts, updates, deletes. But then, instead of the begin commit phase 1, you have a begin abort. And then this is followed by log records that describe how DB2 is undoing everything you did. And then when everything is done, you get the end abort record. This is what it looks like. This is the first half. So up until this point, it looks like the first example that we had, but now we say rollback, and what DB2 now needs to do, it needs to follow that chain here on our right-hand side in reverse order, and for every log record that has undo information, it basically reverses the changes, and it will write a new log record that describes what it is doing. So the first thing that DB2 will undo is our update record, because that's the last thing that we did before we said rollback. So what we will see on the log is another update record. And this update record has the compensation flag on, which means that this is something that, it's not something the user did, but it's something that DB2, this update was done by DB2 to reverse a previous update from the user because of the rollback. And this update record has a pointer that points to the log record that is being compensated here. This is this pointer pointing to log record 0800. And once the update is undone, we will of course have to undo the insert, or DB2 will have to do it. And in order to undo an insert, DB2 has to delete something. So you will actually see a delete record, which is again flagged as being a compensation record, pointing back to the original insert that is being undone by this record. And then there's another delete record because we did 2 inserts. And then we have our end abort record indicating that this is now the end of the transaction. And this is actually what you will see on the log. So for something that you roll back, even though logically you didn't do anything, nothing was logically changed inside the table, you suddenly have twice as many log records compared with the transaction that we committed. And this is part of the reason why doing a rollback can take a very long time, especially if you have a lot of inserts and updates done in the transaction, because of all this extra work that DB2 needs to do. On the plus side, if you ever need to recover this table space, DB2 just needs to follow these log records and apply everything in forward direction, because these log records not only represent the original changes, but also the process of rolling them back. So DB2 already did the heavy lifting once, and now that everything is in the log, we could easily recover this table space, and it would actually forward recover the rolled back transaction and then undo everything, because that's what's in the log. Well, but this is basically just an explanation here how DB2 will do a recover process. I guess everybody really knows what's going on. So you start the full image copy, you apply everything that contains redo information in forward direction. Maybe one thing that's important, when you do a recover, as DB2 is applying log records, it will also keep track of which transactions open and close, because when DB2 arrives at the desired recovery point in time, it needs to know if there are any transactions at that point in time which have neither been committed nor rolled back, because these need to be backed out from the table space, because they're basically cut in the middle. So we need to make sure that nothing from these transactions appears in the final table space after the recovery operation. So this is the most interesting aspect of the recovery operation, that DB2 actually has to keep track of these transactions and, if necessary, undo those remaining changes there. Now, we have only talked about table spaces so far. What about indexes? DB2 also writes log records for indexes, and that includes indexes that are defined with copy no. Now, some people wonder why DB2 does that. Why does DB2 write log records for indexes that are copy no? You cannot recover these indexes. There's no image copy for them. Well, the reason is, even though the index may be copy no, DB2 still needs to be able to roll back changes if you ever roll back a transaction. If DB2 did not write log records for the indexes and you roll back a transaction, DB2 wouldn't know what to do with the index. So all that it could do is put the index in rebuild pending state, and nobody would want that. And that is why we always have log records for the indexes, even if it's a copy no index. And I already mentioned that the index log records describe the addition or deletion of keys or root pointers, but also things like structure changes. Sometimes DB2 needs to split a page into 2 pages. This goes to the log. And a couple of other things, including the automatic index cleanup, which is an asynchronous process that runs in the background and removes dead writs from your index. These also go, these changes that are not really triggered by any user, but by DB2 itself, they also go into the log, of course. Now, lobs, with lobs that are logged, you see log records for space map changes inside the lob table space, and also for the data itself, obviously. But even if your lob is created with a log no, DB2 will still write some log records for it, namely the ones for the space map changes. And since DB2 never updates lob values in place, if you update a lob, you always get the new lob value in a new set of pages. And when that is done, DB2 will simply mark the old lob value as reusable, can be overwritten. And that is why, by simply logging the space map changes, DB2 can always roll back a transaction even if the lob itself is created with log no. DB2 will simply mark the old value as being valid again and the new value as being invalid, and that's a very simple change in a lob space map page. Table spaces with log no, it means that DB2 doesn't write any log records about data changes, and that improves performance, but it also means that you can never do a rollback. You can not only not do a recover to current, but you cannot do a rollback. If you do a transaction on a log no table space and you do a rollback, the table space immediately goes into recover pending state, and you need to recover to an image copy that you hopefully took before. I kind of want to skip the part about checkpoint records because I mentioned most of it, and we have about 12 minutes left. So I want to show you how you can really use the information in DB2 log in order to, for example, find out who changed something in a table. Let's have a look at the table DSN. Well, the schema name differs from DB2 to DB2 version, but the table EMP is a sample table from IBM that has a couple of employee records, including salary information in it. And let's just say somebody changed something in there. There's something that doesn't look right, and we want to know who made that change. Now, DSN1logP doesn't really allow us to filter by the contents of the column. So we could not say, show me the log records where the last name equals Smith. That's not how it works. So we need to have a different approach here. Also, the data change records themselves, there's no information about who did that change. So there is no field for the user ID, for example. But there is a field for the user ID in the UR records. So we need to actually look at both the data change records and the UR records. And on top of all that, everything is binary data, so it's not really human readable unless it's episodic text or you know how to interpret, for example, an integer or decimal value. Before we look at the log records, let's make some assumptions. Let's say we are looking for a row that is still in the table. Let's also say that the table space is not compressed. And let's also assume that the physical row position has not changed, for example, through a reorg or something like that, after the change was made. Let's say that this is the record that we want to look at. So there is this one sample employee, James Walker, and we notice that his salary seems higher than it should be. And we detected that, and we would like to know who is responsible, who made that change, who changed that record that represents James Walker in our sample employee table. Now, how do we do it? First of all, we need to determine the internal IDs of the affected row. And that, of course, that includes the DB ID and PS ID. They're easy enough to find out. They're in the catalog. But we also need to figure out the physical position of the row that was affected. And you see that little select statement here. We're using the RIT function. And we use that in order to figure out the physical location. So by saying select RIT of that table name, where empno equals 000190, which is James Walker's employee number, we get a big int result. You can see that here. The first 3 bytes, we can ignore those. The next 4 bytes are the page number, and the final byte is the slot number inside the page. So we need to look at page number 2, row number 11. We also should be able to approximately see when that change was made, because we want DSN1 log P to finish quickly, so we don't want to go through 48 hours worth of logs. So if we have a small time frame, that's better. So we can run DSN1 log P with that information. I'm using an example for DB2 version 10. This is why the RBAs are 6 bytes here. We can limit the time frame by saying RBA start, RBA end, and we can specify filters DBID 0106, OBID 4. The parameter is called OBID, but it needs to contain the PSID of the table space. And then we say RIT, and this is the value that we got from our RIT function. So page number 2, slot number 11. The RIT here is a 5-byte value. The first 4 bytes are the page number, and the final byte is the slot number. And we also say subtype 1, and that means only undo reader records that represent basic data page changes. So this is our first DSN1 log P execution. And what we get is something like this. DSN1 log P, first of all, we can see that it converts the LRSN to a timestamp over here. This is very convenient. We can also see the URID inside that log record. The log record itself does not contain information about who did that change, but it does contain the URID, and that allows us to dig deeper. You can also see some episodic text here. You can see James Walker in readable text here, and that tells us that we're looking at the correct record. What we can also see is the salary, and this is a decimal value, and this is a field that was changed from 20,450 to 40,900. Now, when I made this example, it took me a while to figure out why this number looks like this, because what you would expect is a decimal basically contains every digit in a half byte. So I was expecting something like this for 20,450 and something like this for 40,900. But instead, you can see that the bytes seem to be shuffled here. And the reason for that is that there's an edit proc on this column. It's a sample edit proc that is used for quote unquote encryption. And DB2 logs physical changes. So these are actually the bytes that were written to the page, and this is what they looked before the update and after the update. And due to the edit proc, the bytes are out of order. So this is why we don't actually see the standard representation of our decimal value, but the bytes are shuffled in this log record. But you can still see the 9 and the 4 and the 2, so we are looking at the correct log record. Now, we need to run DSN1 log P again because we are interested in who made that change. And we did get the URID from the data from the basic data page change log record. So we run that again, and we just remove all the DBID, OBID filters, and we say, just show us everything from that URID. And we know that by using that filter here, the first record that we're going to see is the begin UR record. And this is the result. We actually do see a begin UR record. And the begin UR record has fields for a couple of, let's call it meta information. It includes the user ID, the plan name, the connection ID, the correlation ID, all these things that you only have once per transaction. So DB2 does not need to lock the user ID with every insert and every update. That would be a waste of space. So we can lock that information in the begin UR record, and it'll stay the same for all the records that belong to this UR. And this is how we can find out who did that. It was user Kai. Well, who would have guessed it? It was me all along. So I was using plan name ADB, so you can probably also tell that I was using the DB2 admin tool to make that change, because that is the default plan name for that. And a couple of other things that we see here. So this is basically how you can find out who made a certain change to a record in a table. And you will hopefully agree that it's not exactly trivial. I mean, this is a very simple example, but you still have to kind of know how you need to run DSM1LogP and what parameters to use and what your tables look like and all that stuff. So it takes a little work. Just real quick, and this is going to be the final 3 slides of this presentation. Let's revisit our assumptions, because in the beginning I said we are looking for a row that still exists. Now, why is that? We want to use the read function that I showed you in this little select statement here, because if the row has been deleted, there's really no practical way to figure out what the physical position of that row was. If the row still exists, we can use the built-in read function of DB2, and DB2 will tell us the physical location of the row inside the page set. So this is very useful because we need to use that as a filter for DSM1LogP. That's why I said we want to be looking for a row that still exists in the table. I also said we're going to assume that the table space is not compressed. If the table space is compressed, remember that log records contain binary data. They represent the raw binary changes to the pages. So if the table space is compressed, the log records are also compressed. And if the table space is encrypted, so are the log records. Encrypted through edit procs, by the way, not with the dataset encryption. And that is why I said we want to assume that the table space is not compressed, because if it were compressed, we would need to decompress the row. And in order to decompress the row, we need to have the decompression dictionary, which is not in the log record. So we would need to retrieve it from the table space itself, maybe from the vsem. However, a reorg can change the compression dictionary. So maybe the dictionary that was used when the log record was written is not the current one. So we may even have to go back to older image copies and get the correct dictionary. And this is just why I said, let's just assume it's not compressed. It's also the reason, by the way, why a lot of log analysis tools have slight problems when table spaces are compressed and you want to process older log records. That's the reason. And finally, I said we're going to assume that the row has not moved physically since the change. A row can move, for example, when you do a reorg, the row physically changes position. The problem is if the row has moved, the read function will no longer work because it will return the current position, the new position, but the log record that was written maybe 3 days ago will still refer to the old position before the reorg. And this is why I said we're going to assume that the row is still in the same physical position as it was when the change was actually made. So a lot of restrictions, a lot of assumptions here that we need to do, and it's still pretty complicated to figure out who changed something in a table using DSM1LogP alone. And this is the reason why DSM1LogP is basically the only tool that comes with DB2 that allows you to do anything with a log. And this is basically the reason why if you're really serious about log analysis, you probably gonna need a vendor tool. And spoiler alert, we are a vendor that makes a log analysis tool. So if that is something that you ever need to do, feel free to contact us. This is the end of this presentation. Thank you for your attention. Now, Martin, I have not kept an eye on the chat. If there are any questions during the presentation or any, I don't see any, but
I've been watching it, and there's one question actually, just
okay.
A new one, I believe. Are there best practices to size the output log buffer? And the other one is.
Oh, okay.
And the other question, both from Chuck, are: does an SQL 803 create log records? I believe the 803 is that the multiple insert of the same key into a table.
Right. So the first question, the honest answer is, I don't know. I have not looked into it. You should be able to change it somehow, I guess, but I'm not even sure if there's a ZPARM for that, or maybe you can change it. I'm going to be completely honest. I have not looked into it.
I believe
maybe
there
it's
is a
just
parameter. There is a parameter for the output log buffer. Yeah.
Okay.
I generally try to make it larger than the defaults.
Okay.
The reason being is that when you write the log buffer, then you're writing fewer times to the log. But
true. So you can avoid some of the I/O, of course, and you can write bigger chunks with each synchronous I/O that you do. So yeah, I guess you want to have it a little. I don't even know what the default is, honestly.
I can't tell you what it is for DB212. It's been a number of years since I worried about it. But the other thing is every time you have a commit, you basically have a synchronous force right to the logs.
Right.
To make sure that it changes route. And the parameter is outbuff, and I don't know if Isaac knows and it's fixed in the DSN master address space. Yeah. As for
you got me on this one. I do not know.
And on the 803, I can't. I don't know if the
well, that is actually something that I know.
Yes. Yeah.
At least I know it for. I think I watched the behavior in DB2 version 10, and I hope they haven't changed it. So what I have witnessed is that if you are violating the primary key, then I believe DB2 will not write any log records for that, because that is something that it checks before it starts doing anything.
Yes.
But there could be other unique indexes on that table as well. So if you are not violating the primary key with an insert, but you are violating a different unique index, then what I saw on the log is that DB2 will do the insert in the data page of the table space.
Yes.
It will then do the adding the new key to the primary index.
Yes.
Maybe also add keys to additional, maybe non-unique indexes that you have. And then when it would be time to add the key to the other unique index that you're violating, that's when DB2 notices, oh, this is not going to work. And you will actually see that transaction or this change being rolled back, and DB2 will undo the key inserts by deleting the keys or marking them as pseudo-deleted, and then also deleting the original entry, the original insert into that data page. And so you are you could be creating a couple of log records.
Yes, I think it's safe to say that there would be some log activity in and around the one table. And of course, if any other tables were updated before the 803 is changed, of course, the entire transaction is rolled back.
Yes, and there could be triggers, and there could be, well, an insert does not cascade, so that is good. But there could be triggers that cause other things to happen. There could be a lot. There could be, now that I think of it, there could be maybe a couple of hundred log records if you have a complex table structure.
The DB2 transaction environment is complex indeed.
It is. And those are very good final words, if I might add that.
Well, great. Well, thanks so much for your valuable information. It's been it's nice to see it's nice to see this information again. It's been many years since I delved into it, but I used to teach a class on this in 1988.
Oh, okay.
In 1988. It's changed a little bit since then, but the diagnosis guide and reference, you really need to see it. You can find all that stuff in there. So let me ask.
The log records, it's mostly the DSN DQJ00 member that you want to be looking at. The diagnosis guide is great for the layout of the data pages and index pages. I think there's not too much in it about the log structure itself.
Right.
But you actually need both. You need the diagnosis guide and the DSN DQJ00.
Yeah. All right. Let me. I better take back control here so I can ask our final questions. So let me do that right now. I will make myself a presenter again. And you should be seeing a picture of yourself again on your screen.
I do.
Oh, good. I got that.
That handsome devil.
Oh, yes. Yeah, you look marvelous. So here's our final question, which is always our big question for the day. Did you learn anything today? And I know people are voting quickly because it's into that special time in the Eastern time zone here where we all go and have our lunch. So let me just share that 100% of our audience learned something, which is fantastic. We like to see that number. All right. You've done good. And
I hope that does not mean that only one person voted or something like that.
No, there's a number of people that we had a number of our 61% of our audience voted. So,
Right.
but it's
well, that is good. May not be something that you need in your day-to-day work, but it's something. It's always good to know, I believe, to know what makes DB2 tick, and the log is a really important piece of.
Yeah, if you want to be a DBA and understand recovery, you must understand the log, and that's why this presentation is so important. So with that, I'm going to get ready to cue the music here. I just got to click the right button to find it, and I'm going to thank you so much again for a valuable presentation. And
thanks for having me.
Have a great weekend, everybody. If you're an LUW customer, and I know many of you are, we look forward to seeing you next week for our first LUW show. Thanks again, Kai, and we'll be posting everything on the replay blog, hopefully with the slides as well. Take care, and bye-bye.
Sounds great. Thank you, and bye.